All right, let's start class for the first time. Nothing happened. Oh, some writing. Let's begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you for the students and their patience. I pray that they would study very interesting examples and to learn lots of things about your creation this semester, Lord, as we study partial differential equations and a little bit about physics, Lord. In my prayer. Amen. All right, so, yeah. How about this example? Y prime prime plus 9y, minus 9y rather, equal to 0. Okay, so we've got lambda squared minus 9 equal to 0. That's our characteristic equation. We factor this thing, right? And that gives us lambda 1 equals to 3, lambda 2 equals to minus 3, and therefore my general solution has the form y equals c1 e to the 3t plus c2 e to the minus 3t, right? That's a general solution to a constant coefficient problem. Now, if I'm given initial data, I know, because of existence and uniqueness theory, that there is a specific and unique choice of C1 and C2 which will fit that initial data. I know that for sure because of theoretical results, which we can prove, but we won't prove in here because we have more interesting things to do, is one answer, but I mean, there are various answers as to why we don't do that, but I'll leave this to you. Y of 0 is, what do you want? 2. Okay. Y prime of 0, what do you want?
7.
7. I'll take it. All right.
Not a variable.
So 2. 7 is not a variable.
Yes,
Oh,
those
curses.
lectures.
Joe.
I saw them.
C1 plus C2. He's so proud of not having to vote in this presidential election. Let's see here. C1 plus C2. And then that's 3 C1. He's saying, I'm Australian now. I don't care. Minus 3 C2. It's like, not cool, Joe. Not cool.
Citizenship is still here.
Yeah, really. I guess if there's an election that you're going to sit out, I can understand it. I mean, I'm not going to sit it out, but I understand it. People who want to. Let's see here. Adding equations and subtracting equations is not as much fun here.
Sorry.
I guess my natural inclination is to take this one, multiply it by 3. I mean, it's 2 equations and 2 unknowns. You solve it how you want, folks. But you subtract these things, you get 1 is equal to minus 6 C2, right? So therefore C2 is minus 1/6, right? And what's C1 equal to? 2 minus C2, right? So 12, 13/6. If I haven't made a mistake, have I? Oh, we can check here shortly, right?
You're good.
So what do we got? We've got y is equal to 13/6. Where was I? E to the 3t minus 1/6 e to the minus 3t. Again, I wasn't worried whether or not I could solve those 2 equations and 2 unknowns. I knew I could because of the existence and uniqueness theorem for the initial value problem for constant coefficients. But that said, there is a better way to do this with, like I said, hyperbolic technology. I don't know, like I said, what I'm referencing must be some kind of dream or some kind of, I don't know. Let's hear. So, hyperbolic technology, same example. So you get something like lambda squared equals to 9, so lambda is plus or minus 3, right? And for those who know, this you can solve with y is equal to, let's say, b1 cos 3t plus b2 sinh 3t, right? Now, what's the advantage of this formulation of the solution? Well, let's take the same initial conditions, right? Like, how do initial conditions get applied to the hyperbolic solution? You're like, well, I don't need hyperbolic solutions. I already have exponential solutions. Well, that's kind of true, but at the same time, I hope you can appreciate that this is by far a more efficient machine here for this problem. Right? So that's like B1 sinh of 0, 0. Right? So y0 is b1, which is whatever it was, 2, I guess, right? And y prime is 0. Well, that's, what is that? That's 3b1 sinh t, sinh is 0, right? Plus 3b2 cosh of 3 times 0, which is 0, right? Now, I don't usually write down, you don't, I mean, if you understand what's going on here, you don't really need to write this down per se, because that's 0, but, so what do we find? We find that 7, right, is equal to 3b2. b2 is equal to 7/3. And so there you have it. Y is equal to 2 cosh 3t plus 7/3 sinh of 3t. You see the difference in terms of the difficulty of the algebra here. Cosh and sinh, well, we didn't have to do equations and unknowns, right? Then it's in kind of a nicer way to formulate the solution here. Now, keeping in mind, of course, that cosh is what? It's 1/2 e to the 3t plus e to the minus 3t, right? And the sinh is what? It's 1/2 e to, I just want to assure you guys, it is in fact the same thing we're looking at here, right? So you just do what? You collect e to the 3t and e to the 3t, you got 1 plus 7/6. What's 1 plus 7/6? 6/6 plus 7/6, 13/6. Yep. And on the other hand, the minus 3t terms, you got 1/2, you got 1 minus 7/3, or excuse me, 1 minus 7/6, which is minus 1/6, which is, it's the same animal. All right. Okay, so I wanted to show that to you guys because I thought there's a good chance that you haven't seen the cosh and sinh solution presented in this way. So
It's
nothing
not really that much different.
No, it's not that much different. It's just you know, I don't want you to have the idea that I'm doing something different. It's the same thing you already did. I want you to understand it's just a nicer way of attacking these kinds of problems. Now, initial conditions are kind of boring because, well, they always work. But let's see here how things can go awry. So I want to talk to you not about initial conditions now. I want to talk to you about what are called boundary conditions. All right. So I just wrote up because I noticed that as I was, I've gone through various stages in my teaching of PDEs. Usually I only have like 2 weeks to teach it at the end of the 334 course. So what I do, I run through examples and I just basically show 3 or 4 complete solutions to like a heat equation, a wave equation, a Laplace equation, whatever else time allows. That's kind of it. But in the process of doing that, I find myself, if I'm complete, like there's 2 different ways you can show the solution. You can show the solution in a way that you just do what's needed, but that begs the question, like, how did you know the other cases didn't appear? So it takes a fair amount of discussion to explain the cases which don't appear, which aren't relevant to the boundary value problems, why they're not relevant. And so it's occurred to me that it's a good place to let theorems be used, because if I just write down a couple of elementary theorems about standard boundary value problems, then we can refer to these theorems, and I mean, you should be able to derive what I'm about to do, but at the same time I want you to be able to reference it rather than reinventing the wheel when we get to problems where this problem appears again. Okay, so I'm just presenting a few theorems basically of common boundary value problems that we face. So, but I'm not stating it as a, I'm kind of doing it upside down. What I'm going to do is I'm going to state the problem, we're going to find the solution. Once we do that, then I'll state the theorem that we've just derived. So it's not, not the usual exposition in math either, I suppose. Oh, we're not doing ODEs anymore. Although what you're going to see, guys, as we go on in this course is that ODEs, pretty much everything we do, almost everything we do, it comes back to ODEs. Like, yeah, you have a partial differential equation, but you do something, and then you face an ordinary differential equation or something like that. It's a lot of techniques are like that. Okay, so here it is. Here's the problem. I think I've told you guys before, mathematicians are kind of a strange creature. We're only happy if we have problems, you know. It's our defect. Let's see here. Determine which values of k that's supposed to be a k, allow solutions of y prime prime plus ky equals to 0, subject the boundary conditions. So I'm going to write this out once, boundary conditions. So what we like to do is use abbreviations, so those are going to be BC, boundary condition, all right? What are the boundary conditions that I have in mind? Y of 0 is equal to y of L, all right? And we're supposing y is a function of x, and we're looking at 0 less than or equal to x less than or equal to L. That's our context. That's what we're looking at. Now, let me point out some obvious differences in this problem already between this problem and what we were just looking at. This k, right? What happens as k changes? A pair of examples I just did, we had a single differential equation. It was fixed, right? And then we looked at initial condition, found a solution. So what I'm kind of doing here is I'm fixing boundary conditions, right? And I'm not assuming that we have one differential equation. We're about to find out that if we just looked at one differential equation, odds are pretty good it's going to blow up on our face and not work. It's kind of like if you give a collection of points and you say find a circle which has these points on it. Well, there's nothing to guarantee that a collection of points are going to fall in a circle, right? So it's more like that. You know, so what's the big difference here? The big difference is that we're saying we're comparing x equal to 0 and x equal to L. The data's at different independent variable values, right? Before we were looking at time 0 and time 0. I changed the name of the game a little bit, right? I'm using x instead of t now. Don't let that distract you. That's not really the issue at all, obviously. I mean, that's just a letter. We could go back and do the first two examples with x's. Oh well. I refuse to stop the tape and start again just for the sake of making that modification. But maybe that would be, you know, if all I did all day long was to make better and better YouTube videos, maybe I'd do that. I don't know. But, I don't think there's any future in it. I mean, you need like million subscribers to make money on this junk, you know? Yeah. I'd have to actually monetize my channel first, and so I don't think I'm going to do it. I mean, if I got fired, I might just like pour everything into it. But let's hope I don't get fired. I don't think I should be. Let's see here. So, I'm sorry, we actually had a problem to work on. So, k is a real number, right? So you got choices, 3 choices. This is the trichotomy. K equals to 0 is one choice, popular choice, right? So if k equals to 0, what we got? We got y prime prime equal to 0. And so what's the general solution? Y is equal to c1 plus c2x. Integrate twice. Or refer to the constant coefficient solution, whatever floats your boat. Now I got to apply the boundary conditions. So we got y of 0 is c1, which by the way that's one thing, right? And what's y prime of 0?
Just be C2?
Yeah, exactly, c2. And apparently those need to be, oh, I'm an idiot. I'm an idiot. Why am I doing 0 for both? Why am I differentiating at all? Gosh. Oh man. Oh, is that how this semester's going to be? Oh no. Oh no, no, no.
Technically, you're still in the summer semester, so it doesn't affect your fall.
I know what you're talking about. I wouldn't be talking about a...
Oh, sorry.
Yeah, it's in the semester.
Sorry.
Y of L is equal to C1, right? Plus what? Plus LC2, right? Plug into here. Now these are equal. So what's that say?
The C2 or L.
It says, yeah, it says L times C2 is equal to 0, right? But we're assuming that L is not equal to 0, otherwise this is dumb.
C2 is
So,
equal to 0.
okay.
So therefore C2 is equal to 0. Alright, and what else then? Well, if C2 is equal to 0, oh, okay. Alright, so let's put it all together then. So we could get, so basically this, we get Y is equal to C1.
Convenient.
There is a constant solution to be found in this case. And if you stop and think about that, that makes total sense. Right? This could be like a spring. Right? If you think of X as being time for a second, if you can do that. Right? Imagine X is time, then this is a simple harmonic oscillator. If you have the simple harmonic oscillators at the same position at different times, then it's oscillation. Well, unless what? Unless those times are, well, certainly one possibility then with that interpretation is that it's a constant solution. You can see that there are others if you start thinking about periodicity, right? Like you could have matching positions provided that the times are off by an integer multiple of the period, 2 pi. Let's get to that. Let's let the math get us there. Let me not try to... the way I'm reasoning right now is not optimal. Okay, so continuing with our straightforward mathematical trichotomy, what's the other choice? How about k greater than 0? Right? So if k is greater than 0, we can say k is equal to beta squared for some beta greater than 0. So why would I do that? The reason I'll do that is because that tells me that the problem I'm facing is what? It's y prime prime plus beta squared y, right? But you guys know differential equations, so as soon as you see this, you recognize this for what it is, which is lambda equals to plus or minus I beta. Right? In other words, the solution here, using ODE stuff, is just y is equal to C1. The C1 and C2 are disposable for me. After we get to the next case there, do core dump or whatever it is that I don't know, I've been taking computer science a while, I know what the proper terminology is. Turn the computer on and off. Oh, so it hasn't changed since my day. Alright, good.
No, that's IT.
Here.
It's the IT department.
That's the world-class IT department. Okay, so sorry. Oops, shout out to IT. Let's see, your C2, sine beta x. I was tempted to do a shout out to the physics department during orientation, but I didn't do it. But I thought about it. Because like the guest presenter was talking about the physics department, or physics, as if it was in a department, and it occurred to me it would be rather funny to just go, shout out to the physics department! And just in the middle of it, but I don't know,
You hate physics.
I actually didn't hear her say that because I was calculating. So. But it was told to me later that she mentioned the physics department, so like, okay, that's good. And that's actually a good example of why it's important that I don't listen to those talks, because if I did, I might do something like that.
Yeah.
And then
And you'd have to become a YouTube star.
then yes, that might require me to think more seriously about how to be an evil capitalist on YouTube. Let's see here. I don't know, I guess we haven't decided if capitalism is evil yet. Ask me again in November. Let's see here. So
We already decided math is evil, so it would just be redundant evil.
well, I have mentioned before that I do think that mathematicians are Sith because we
Oh
do
yeah.
believe in absolutes, of course.
Yeah.
But, yes.
That was
Why?
last time.
Yeah. Where was I? Oh yes. Boundary conditions. So y of 0. Sorry, I'm kind of silly today. C1, y of 0 is C1 because sine of 0 is 0, right? And y of L, well, that's equal to curses. Dang it. Oh, I feel like I'm doing something wrong. Sorry.
You're doing it like the previous problem and just plugging in L and then setting it equal to C1.
Well,
Real and hard to solve.
it seems to me like I'm assuming that this is equal to 0 as well, which is, in order to say what I say in the notes, I think I'm assuming that. I haven't read it, but, like, okay, so what I'm about to get to here, if I don't assume, we can do it. Y of L will be what? It'd be C1 cosine beta L, right? Plus C2 sine of beta L. Yeah, I think I want to put a 0 there. The reason for that is pretty simple. If I assume that they're both at 0, right? Then this says what? So if y of 0 and y of L are both 0, this says that C1 is equal to 0, right?
Oh, yeah.
And then this becomes manageable C1 0, and this other one then is what? So 0 is equal to C2 sine of beta times L. I've been doing this all wrong all along. I can turn this silly monitor over and kind of see where I am. I am my own cameraman. Alright. Okay, so anyway, but then the question is, how can that happen, right? We're interested in finding non-trivial solutions, of course. You could put C2 equals 0 and 0 is always a solution.
Yeah.
Alright, but that's not the interesting case. The interesting case, of course, is when this is 0, how can that be 0? How can you get 0 without C2 being 0?
Well, the sign of
Sign.
BL equals 0, so L equals 0.
So this equals 0, but...
Or B equals 0.
Well, L equals
Beta.
0, we're not allowed either.
Beta equals 0.
Beta equals 0.
And that should be the only case, right?
Nope.
Can beta be 0? We were saying it's greater than.
Yeah, beta can't be 0
Yeah, it
also.
has-
Good
it
point.
Has to be.
Beta has to be positive, so that's out.
I don't remember mine.
Yeah, the circle.
Ooh, let's try to
Alright,
back to
so I'll help you with that. So sine is 0. If we have sine of something being 0, that means that beta L has to be equal to n pi.
Oh, you were doing actual trig. I was thinking hyperbolically.
Ah.
Oh, that would be why.
Oh.
I'm like,
Oh, you're thinking
Yeah.
you're thinking cinch?
yeah.
Yeah,
Please don't think I'm much more stupid for my comment.
If it
of
was
thinking they're
no,
not being
if it was cinch, you're on the money. 0 is the only solution, in fact.
Okay, that's what I was.
I just couldn't remember the units.
That will be relevant to the third and less interesting case of this trichotomy. But so there it is, and that tells us that beta is equal to n pi over L, and hence the k, right? K is equal to what? Well, k is equal to beta squared, right? So n squared pi squared over L squared, right? So it turns out, all right, we don't know if that, we're not sure yet if that's the end of the story. It turns out it is. But it looks like then there's not just one differential equation in this infinite family that's parameterized by k, which works for these boundary values. There's in fact infinitely many, countably many. Right.
Wait, just to clarify, L is also a real number, right?
Yes.
Or any real number?
Yeah, L is the length
Okay.
of something we're looking at. Okay.
What was the whole point of like having like beta squared? Like why not just leave it as beta?
Oh, because otherwise I'd be working with square root of k, square root of k, square root of k, square root of k,
Oh,
square root of k,
okay.
square root of k. So just it's a convenience of exposition. And again, if k is less than 0, so then k is equal to minus beta squared for some beta greater than 0, right?
Mm-hmm.
And so that means what we're looking at is y prime prime minus beta squared y equal to 0, which by the way has solutions. Y is equal to stiff. Y is equal to a cosh beta x plus b sinh beta x. So again, you feed it 0. You get a cosh of 0, which is 0. 1, rather. Sinh of 0 is 0. So that forces a to be 0. And if you look at y of L, well, that gives you b sinh of beta L equal to 0, which implies that either b is equal to 0, in which case we have the 0 solution, which by the way we already had up here in case 1, so we've been there, done that. Besides, technically it's not allowed in this case. Ignoring the fact that we already had it's also not allowed here, we said k is less than 0. Well, sinh is everywhere injective, it's always increasing, and it's only 0 at 0. Sinh of 0 is 0, no other thing can we put into sinh in the real domain and get 0. Complex domain, another story. Oh, that comment's directed to you. Okay. So,
I want that correct comment.
but you're safe for the
I
moment.
also redirect it to you.
But we'll probably get back to that kind of stuff, whether we like it or not in here. I mean,
Okay.
the problems lead us to complex sine and complex cosine, cosh and sinh.
Okay.
That's, I mean, you can't, they're two sides of the same coin.
Yeah.
Like, it can't be avoided. You're going to solve problems robustly. Okay, so anyway, the point is, there's nothing here.
Right.
So, answer, theorem. Y prime prime plus ky equals to 0. Subject to y of 0 equal to y of L equals to 0 for 0 less than or equal to x less than or equal to L has solution. What does it have solution? Has solution. Let's see here. Y equals to, let's see here, what do we got? C1 was 0, C2 was whatever, right? So actually, if you look at it, the solution is y is equal to some constant, let's say a, sine of what? Sine of beta x, beta was n pi, so sine of n pi x over L. Where, let's say only if k is actually equal to what? K is actually equal to n squared, pi squared over L squared. For some So I think in my notes I call this proposition 8.3.1. So, you know, this will be nice to know about when we're going to face this boundary condition problem as we solve PDEs. It's going to happen, okay? So yeah, I'm a little bit of patience on your part. I know in isolation perhaps these problems aren't that interesting, but it'll allow us a more streamlined presentation when we get to the more interesting PDEs to be able to refer to these results. It'll make our discussion much more compact. Otherwise, when we come to this problem, logically we have to go through all of this.
Right.
And there were a number of years where I just labored through these 3 cases every time I had a problem.
Oof.
It's not, I mean, after a while you get good at it, but at the same time it's terribly inefficient. So let's just try to take a step back. And now this is a little bit sneaky. I've rolled in the 0 solution to n equal to 0, because like sine of 0 is 0. And in some sense it's redundant. Like you could just throw out, you could safely, you'd lose no solutions, no possibilities, by just saying n is an element of n union with 0. Despite the claims of some students, 0 is not a natural number. Sorry. Sorry. Yeah, I guess it depends on what country you're in. But, okay, so yeah, that actually would get everything. The negative ones, negative values of n, what has happens there? You get the same k's, and you get minus with the sign because sign's odd, you know. So if you want to capture all possibilities, that suffices. Okay, what would you next try in terms of boundary values? What would be another? How about same song and dance, but instead of matching endpoints that are 0, how about 0 velocity endpoints? How about instead same almost the same problem, but let's add some primes here. Oops. Where was I? Someday somebody's going to build a robot to do this for us. Let's see here. Actually, that day's probably now, but I'm too cheap. Okay, so that and that, right? So that's the next problem. Like, if you have some intuition here, you kind of expect what's going to happen. If you think about why this theorem is true in terms of a spring, it makes a lot of sense. But without the primes, what it's saying is that if you're looking at a spring and it has, you know, at one time and then at another time, the times being different, it's at the resting position. What's that mean? That means it's either resting for all time, n equal to 0, or those 2 positions, I should say positions, I should say they're 2 times at 2 different times. It's at resting position. What does that say about the times? The times have to be, you know, some multiple of the period of the system apart.
Yeah.
So that's why this theorem is here. I mean, what's the period? Switching to t for a second here. I mean, maybe I'm discovering something pedagogically. I should, instead of putting t here, I should put like a capital T for like period, you know? Because that's what the role is it's playing. When, you know, when L is, well, how do I say this? I mean, for this to be 0, you need t to be a multiple of L. In other words, this L has to be some multiple of the period for the system. Anyway, I'm gonna stop talking. The math is clear. Whether or not you understand what I'm jibber jabbering about right now doesn't really matter. Again, I'm fighting my. I'm starting to, as I'm talking to you guys, see an interesting, more interesting exposition of these things that could be made. All right. Okay, so here we go. Now, again, we've got y is equal to c1 plus c2x in the k equal to 0 case, right? And so, but y what? Y prime of 0 is c2, and y prime of L is what? It's c2. c2. Okay, so the 0, 0. And so we get y is equal to c1, okay? And that could be a non-trivial solution this time, actually. Last time the constant case was forced to be a, trivial thing. K greater than 0. All right. Again, we'll let k equal to beta squared, right? And so we're looking at y prime prime plus beta squared y equals to 0. Our general solution has the form y equals to like a cosine beta x, right, plus b sine beta x. So that means y prime is what? Gotta get a bigger clock in here. Okay. So y prime then is what? It's minus a beta sine beta x, right? Plus b beta cosine beta x. Now we plug in our conditions, right? So like y prime of 0 is what? Well, y prime of 0, we get no information about a, but over here we get b beta, the product of b and beta is 0. Beta is not equal to 0, by assumption here. Sorry, I forgot to say. I'm assuming, of course, that beta is greater than 0, right? We already covered the beta equal to 0 case. If you want to think about it that way already in the first thing. Once is enough. All right, so beta is positive. That means that b beta, the product of b beta being 0, forces b to be 0. In other words, okay, so y prime of 0 is b beta. B is equal to 0. All right. Y prime of L. Well, that gives me minus a beta sine of beta L, right, equal to 0. What does that mean? Well, I think now it should be fresh in your mind. What's this force upon us? A is not 0. Beta is not 0. Sine of that quantity has to be 0. So therefore, this beta L has to be what?
N pi.
Yeah, n pi for some
Integer.
Yeah. And since we're kind of interested ultimately in enumerating. I mean, that's all possible, right? But in terms of, let's think about capturing solutions which are not redundant. If I want a non-redundant set of solutions, if I just choose natural numbers, then I'm good to go, because the negative n's, what do? Just give you the same solution again, but with a minus. So like just focus on these, you're good to go. Okay, so there is beta, again, is n pi over L. Right, so therefore the k getting back is minus n, I'm sorry, not minus, k is n, come n squared pi squared over L. Oh, did I do that right? Sorry.
L squared.
Beta basically L squared, yeah. Alright, now, again, the third case is kind of boring. Or to quote Daniel, boring. But I'll do it. K equals a what? Minus beta squared, that's the other possibility. Right, K could be negative. So again, we're trying to enumerate all possible solutions to this boundary condition for this family of ODEs. So we got what? We got y equals to a cosh beta x plus b sinh beta x. You differentiate that, you get y prime beta a sinh beta x plus beta b beta cosh beta x by the chain rule. And so, all right, almost done. Y prime of 0 is what? Y prime of 0. Well, y prime of 0 is, that's 0, and this is just b beta. And y prime of L, so this tells me that b is equal to 0, right? Y prime of L, well, that's going to give me b being 0, this is gone. And I just get beta a sinh of beta L, but remember I was just telling you, the hyperbolic sign only has one real 0 in its 0, which is not available to us. So this forces a to be 0. And so there you have it. The third case in the trichotomy got nothing to offer us. And so our related problem has a solution as well. This is what I call proposition 8.3.2. Oh, by the way, for what it's worth, which is about $1, I don't know, maybe 2. I don't know, it's sometimes helpful to think about this as like the nth solution and maybe put like a little some n here or something, I don't know. I'm not suggesting we have a privileged notation there or anything, I'm just, there's an n dependence. Alright, so anyway, what happens when you add primes? Put prime here, put prime there. Looks like, okay, so what happens is the b is 0, so the signs are gone this time, and instead we got cosines. Right. And the kind of cool thing is, again, allowing the 0 case picks up the k equal to 0 case because of the way that cosine of 0 and sine of 0 work. Sine of 0 being 0, so it's, I mean, alright, fine. If you want me to, in the last theorem, 8.3.1, if we just want non-zero solutions, what should we do? We should just even throw out n equals to 0 if you think back to it, right? So just n is a natural number if I'm just looking for non-trivial solutions. And I am looking for non-trivial distinct solutions, really. In the end, we're going to see that's what we're most interested in. So, but here I do need to join the 0 because cosine of 0 is 1, and the constant solution is a non-trivial participant in the universe of possible solutions to this boundary value problem for this family of ODEs. Now you guys can ask a question, obviously. How on earth why would you find yourself faced with a family of ODEs? How does that even happen, right? So we may have enough time today for me to show you how that happens. I don't know, we'll see. But I want to finish these kind of boring, but should be straightforward if you... Are you guys remembering enough 334 that makes sense?
Yeah.
Oh, yeah.
Okay, cool. Ah, mixed endpoints. So what if you have, like y of 0 is 0 and y prime of L is 0? So like this. What if you have y of 0 is 0 and y prime of L is 0? Alright.
Is it something interesting at least? Like,
It's different than this.
okay.
Yeah, we'll see. Alright, so let's work it out. Sorry if this is boring. I mean,
No, I mean, I was just hoping not to like run through it again and get like similar answers like the first two.
you know, I hope it seems boring because I've seen this be a cause for consternation with students who, you know, I mean, in the past sometimes I've taught this material, and this is the part that people get hung up on because it seems so similar. If you just think through it, you don't have to memorize all this stuff either, right? I mean, but again, it's, as an efficiency for us, it's nice to have these results to refer to. All right, yowzers. K equals 0. So we have y equals 2 c1 plus c2x. And what do we got? Y of 0 is c1, which is 0, right? And y prime of L is c2, which is 0. So, oh, there you have it. Okay. Stick a fork in it. There's nothing there. Alright, so how about the other case? Keep it positive, k greater than 0. So we let k equal to beta squared. We look at our friend y equals to a cosine beta x plus b sine beta x. Right? And let's see here. Again, I should emphasize that all of these calculations, we could take x and replace it with t. And that might even be more sort of physically natural, since y prime prime plus ky is a harmonic oscillator if the prime is a time derivative. But anyway. I digress. Alright, so y of, what did I say? Y of 0 is a plus cosine 0. I mean, so a is equal to 0 here. What's y prime of 0? Y prime of L, rather, is b beta cosine of beta L equal to a 0. Aha! That looks interesting. So the question then, of course, is when is cosine 0? So, of course, yeah, plus or minus.
Sorry.
Was it? Oh.
Oh, sorry.
Plus or minus pi over 2, plus or minus 3 pi over 2, you know, so forth and so on.
So
A nicer way
over 2.
A nicer way to express that is that beta L, we need that beta L is equal to pi over 2 times 2n minus 1 for, you know, for n in n and z. Now, oh, okay, so if you think of, we assumed that beta was positive, right? So with that in mind, I can throw out some of these solutions. L is positive, we're assuming that. So if I want this to be positive, I can assume that n is a natural number. To keep it in the case I'm considering. But if you have that condition met, then the cosine of that quantity is 0. So we got solutions. By the way, these are sometimes called Eigen Solutions, for reasons which we'll look at in more detail.
Eigenvalues.
Yeah, there's eigenvalues. Alright, let's see here. So, beta is equal to pi times 2n minus 1 over 2l. So therefore the k value here was what? It was pi squared times 2n minus 1 squared over 4l squared, actually, for what it's worth. honestly forget what happens in the other case. I want to know if we're going to get nothing or something, or let's find out, right?
It's like math Christmas.
I know there's. It's like Christmas. Yeah, it's like just like Christmas morning. Unless you're my brother and you've already opened the presents and taped them back. All right.
Is this recent or when you were kids?
When we were kids.
Last year.
mean, yeah.
Christmas in July. It's over with.
You're like, Santa's handwriting looks a lot like my dad's handwriting. Something's up. It's part of our clue.
Dad must be Santa.
That's actually probably the most clever way I found kids discovering their parents are Santa.
I think they just told me.
Yeah.
Yeah.
Sad.
We don't even do it. Like, we don't.
Yeah.
We have never.
It's
we
probably
don't.
good. I mean, it's
Yeah,
basically
there's
just
nothing to
lying to
gain
your
from it.
children.
Yeah, I think. We thought about it. We're like, it's not really a healthy tradition. Let's see here. So k equals minus beta squared.
Did you send your kids to school telling them to bunk it for all the other kids too?
Oh, we're homeschooled, so let's see.
Oh,
For
okay.
us. Let's see here. K equals minus beta squared. So we've got, of course, beta positive. So this gives us y is equal to a cosh beta x plus b sinh beta x. Alright, so y of 0 is 0. Y of 0 is also a. And y prime, so a is 0. Y prime of L is going to be b beta, or beta b cosh beta L. So that implies that b is equal to 0. Cosh is at its smallest one. So it looks like it's kind of like x squared plus 1, except it's got exponential growth on both sides, right? But the cosh has no zero, no real 0. So the middle case is the only one that paid off, and our theorem is this: y prime prime of k y equals 0, subject to y of 0 equal to y prime of L equal to 0 for this. Has solution. What do we got here? Sine again, right? It's like we're back to sine, aren't we? Because it'd be sine. So like maybe I'd say b sub. Might say it's something like b sub n, whatever, and then but it's not n pi x over L now. It's what? It's pi times 2n minus 1 divided by 2L times x. And it's not k equals n squared pi squared over L squared now, it's what? It's pi squared 2n minus 1 squared over 4L squared. And this is for n in the natural numbers. And this is my proposition, I believe 8.33. I'm starting to get bored of these. Sorry. I shouldn't get bored. Alright. I guess you know what I'm about to do next. Can you guess what my next case is?
Y prime of 0?
Why did I never got cosh and sinh in any solution? What? I don't have cosh. I missed cosh and sinh. Why aren't they coming up? Come on. Oh. Okay. They come up in different ways later. I forgot. It's been a while. Don't worry. They will appear. Just not in these discussions. All right. So I think you know what's happening next. It's one other case. Right. Did I put here?
I think that's the
Y
last one.
prime of 0?
Y prime of 0 equals Y out.
Yeah. Y prime of 0.
Y out.
Yeah, that's the remaining case. I will spare you the details. That's okay. What's going to happen is what? Instead of having sine, you're going to have so nearly the same result, except the role of sine and cosine flip over, basically. You know, like the y of L equal to 0. Makes me the y prime of 0 immediately forces the b to be 0, leaves the a unphased, and then the y prime of 0 it gives you a condition on the other term. Anyway, long story short here, we don't get sine, we get cosine. The argument is the same, and the k is also pi squared times 2n minus 1 squared over 4l squared for some n. Yeah. And again, no constant solution, no zero trivial. The no non-trivial constant solutions allowed. Okay, that's it. There it is. All right. So that's actually the main. That's the kind of ODEs we need for a while in here. That we're going to face a little bit later in the course. We'll run into things where we might transform a partial differential equation back into one of the ODEs you forgot how to solve. That will happen to us just when we think we're safe. All right, but for the immediate, if I'm just gonna, I think I'm pretty much gonna start the course by showing you the stuff that I would classically have taught in 334. But I'm probably gonna stop doing that since I don't think it has happened lately. But anyway, okay, so we got these 4 theorems. Now that we've got that, and we've got a little bit of time still, so let me just show you how we solve, how we do separation of variables. Okay. So actually, I'm going to start and stop the video for the sake of